Okay, we have here today another integral on the board from the UNSW Integration Bee 2023. As you can see, they used that right here in the bounds. This one was from round 2, problem 16. We have the integral from 0 to 2023, the floor of x times the ceiling of x dx. Okay, I always enjoy a problem with the floor and ceiling functions. And I know I did one pretty similar to this. I think there was a problem from the MIT Integration Bee that was very similar. But I think this one works out just a little bit differently. Now, the nice thing we can notice about the floor and ceiling functions is if our bounds were just separated by 1 and they were both integers, like let's say the bounds were going from 3 to 4 or from 0 to 1, let's say, well then in that case, each of these functions can be evaluated to just a number. And then at that point, we can just pull this outside of the integral and the integration becomes trivial because it's just like we're integrating 1. And so what I want to do is use that and break this up into 2024 integrals. So then by doing that, we know that just this part right here is going to evaluate to just some number. So what I'm going to do to start is we'll start with our first one. We'll just go from 0 to 1 and evaluate this. But now the floor in this region is just going to take us down to the lower bound. So for our floor of x in this region, we're going to have 0. And then for our ceiling in this region, we're going to have just 1. And then doing the same thing for our next one, going from 1 to 2. And then here again, because the floor essentially rounds us down, it'll give us the greatest integer less than or equal to x. Well, in this region between 1 and 2, that's just going to be, again, the lower bound, 1. And then here, the ceiling function is going to essentially round us up to the upper bound, which is just 2. And then we're just going to continue this way on and on, right? And we could write this out all the way to 2023. But now from here, what I can do just to kind of make it a little easier on myself is just to kind of generalize, just kind of focusing on any one of these rather than looking at this whole sum. So if I do that and look at a general one of these integrals, and I'll call my lower bound n, just knowing that n is always going to be an integer, well, the upper bound is just going to be n plus 1 because we've set it up that way where our bounds are always differing by 1. And then doing the same thing with the floor and ceiling, it's going to give us our lower bound times our upper bound, so n times n plus 1. And again, just recognizing that we're integrating with respect to x, and these n values are just numeric values. So the integral of this is just going to give us n times n plus 1 times x, evaluated from n to n plus 1. But when we evaluate that, when we plug these values in, what's going to happen is this is going to give us an n plus 1 here. And then for our lower bound n, we're just going to be subtracting off an n. But this is going to cancel, and this whole piece right here is just 1. So this integral is always going to be just n times n plus 1, which is just, again, the lower bound times the upper bound. So at this point, we can recognize this is going to be the value for each of our integrals. And we have, like I said, 2024 of these. So we can actually just sum all these up, put it in a series. Okay, they're all going to be n times n plus 1, just like this. Now we just need to know for this sum what we're evaluating from. Like let's start with the last one. We have our last integral right here. We know our n plus 1 value is going to be 2023, so our n value is 2022. So the upper limit of this series is going to be 2022. And now we could start at n equal to 0, but just notice this first integral, this 0 times 1 is going to 0. So I can just ignore that one and we can actually start at 1 because that's not going to do anything for us. So let's just start this sum at n equal to 1. By multiplying this in here, we can go ahead and we can write this as n squared, and then we can write this as plus, the other value is going to be just an n. And because we're adding these, I can break this into two sums, okay, from the same bounds. So let's just write that in. And now all we're going to need to do to get a numeric answer is just calculate these two sums, but we actually have formulas for both these. So let me just get a little more space and we can finish this thing off. Okay, so like I mentioned, we have formulas for each of these sums. So first, let's look at this. There is a formula for the first k natural numbers. I'm using k instead of n because we already have n here. So the formula for this one is actually going to be just k times k plus 1 over 2. I never have a hard time remembering this one, but I always have a hard time remembering this one, which is the formula for the first k squared terms. So let me grab this formula here. Now at this point with both these formulas, we can actually just plug in our k and simplify and finish it off. But I think I want to do the algebra first, then we can plug in later. It just seems a little easier that way. So I'm going to do here to simplify this. You notice we have k times k plus 1 in common, and we also can take a 2. So I'm going to actually just factor that out, I think, because we have it in common in both these. I'm not sure if that's the best way, but let's just do it that way. And what that's going to do is that's going to leave me with 2k plus 1 here over 3. And then this is just going to be a 1, but I'm going to write this as 3 over 3 because I want to combine these terms. So doing that with the common denominator here, this is going to actually become 2k plus 4 over 3, and then we'll bring over this other stuff. But notice when I do that, we have this 2 here. If I take a 2, I can cancel with this term, and I can cancel a 2 here and cancel this down to a 2. So now it's kind of nice because we've got 3 consecutive terms here, k times k plus 1 times k plus 2 all over 3. So at this point, we'll take the k and plug this back in. So this is going to give us, all we have to do is calculate 2022 times 2023 for our k plus 1 term times 2024 all over 3. And I sure hope that UNSW allows calculators, because this is kind of not that nice if you had to multiply it out. I mean, you could do it, but it's going to be a little tedious. So when I did this with my calculator, what I got for a solution was 2,759,728,048. I was hoping we might get a nicer answer than that, like maybe like 4 or 2023, or maybe pi over 4, but unfortunately no, we had to multiply that all the way out. So that's it, we'll stop it there. Thanks everyone for watching. Please like and subscribe. Have a great day.